Hi there, I'm Art.
And I'm Paolo.
And we're both authors on this paper about waves in particulates. So this is when a linear wave, like a sound wave, it can also be electromagnetic, bounce, scattered between the particles. And I guess if you squint, it could be quantum.
Yep.
And we want to tell you a brief, a very light overview. What the hell is the point of this large paper? Wouldn't write a large paper unless it was strictly necessary. So the main motivation for us came from this figure you're seeing here. This is like a cross-section of a pipe, and there's a particulate flowing through it. So if you work in industry or applications, the particulate could be slurry, an emulsion, a powder. And as they go through, we've got two sensors on either side that are sending through sound waves. They're scattered from the particles, they're bouncing around, and they arrive at another sensor, or some of it comes back. And from those measurements, we want to learn something about the particulate, right? But there was a really critical gap in the theory that we realized without it, we really couldn't be sure these measurements made sense for a broad range of frequencies and even for dense particulates, when that's the case we needed. So the gap in the theory was how the waves interact with the boundary of the material, how they go back and forth between the particulate and the boundary. So we have this beautiful figure Paolo made to help illustrate that. The red shows the waves bouncing between the particles. That is reasonably well understood. The bit that we don't think is well understood was the green part. When I say isn't understood, not done correctly. Yes. It just simply hasn't been done. And if you work with effective theory, we don't want to do this just for one configuration of particles. We're looking at the average response, the effective response, or the ensemble average response to get some effective boundary conditions, and we want to deduce these from first principles. We deduced them from first principles with great effort.
And after this long journey, what we discovered is that there was a simplest way to look at it and to understand it. So this is not the full maths, but just a gist of it. So what we can do to solve this problem is to back off the particles a bit and solve for all the waves in between particles and walls. So what do I mean by that? We want to understand case B on the right, where you have the particles really close to the wall, and there's all those complicated waves that we showed in the last figure. What we do, we back off them by a distance delta, and we leave this artificial boundary where we have these reflected and transmitted waves represented by A and B. And then when we understand how the block on the right of the particles reflect and transmit waves, we can take the limit of them getting really close to the wall again, and we solve the full problem with new effective boundary conditions. And this leads to really simple formulas for us to understand reflection or these transmitted and reflected waves. And now we can start thinking about solving the inverse problem.
So yeah, just as a gist, this method of backing it away, you can repeat this for other geometries. We've only shown it for a plate, half space for simplicity. And the end result is you're going to get linear, explicit formulas to calculate what is reflected and transmitted waves. And thus we filled the gap. And we've got those equations now that could be used to measure particulates. Previously in the literature, there's no one who's been using the wrong formulas. The formulas for a homogeneous medium, completely homogeneous, but in this case you should be using what we've done here. So now we've opened up the door to measure a large range of particulates. Thanks for listening.
Thank you.